Okay. Yeah. So just to kind of introduce people on the general theme, to remind you, we're going to be having a series of 3 to 4 webinars leading up to the summer meeting, where we're looking to scope out certainly the PPAI perspective on what a potential coastal prediction working group would be. And there's a lot of potential elements in that, and we'll discuss that in the closed session after the presentation and questions and answers today. So we're going to start off by just looking at what the current prediction skill actually is of sea level, particularly along the coast on these seasonal timescales. And so I'm happy to introduce Xiaoyu Long, who's currently actually a research scientist in my lab, but Xiaoyu started in atmospheric sciences. He got his master's at Peking University, spent some time as a weather forecaster, so he's had some practical experience, and then went to get his PhD with Walt Robinson at North Carolina State. Then he had after a short postdoc with Brian Mapes at Miami, he moved to Hawaii and did a postdoc with Matthew Wodlansky, looking at this question of sea level prediction. And in fact, what Xiaoyu is going to be talking about today is based on a paper that came out of that work. So without further ado, Xiaoyu, I'll hand it over to you. Remember, it's you have 25 to 30 minutes. At 25 minutes, I might jump in with a warning, if just to remind you, you have about 5 minutes left.
Okay, thanks, Matt, for the introduction. Thanks for having me here to give this talk. Like I said, the talk is about a paper we published last year. So the title of the paper and also the talk is Seasonal Forecast Scale of the Sea Level Anomaly in a Multimodal Prediction Framework. So the paper and the talk has the same title. Is showing here, Seasonal Forecasting Scale of the Sea Level Anomaly in a Multimodal Prediction Framework. So first, why we need to do this? So a few recent studies has shown that the sea level variability has increasingly contributed to the coastal impacts. First reason for that is the global sea level rise, because we have a higher baseline sea level. So the same amount of sea level variability can result in more extreme high water level events. And also, warmer climates, the sea level itself tends to have stronger variability, which have also published a paper on that topic. So there will be a stronger demand on accurate sea level forecast on monthly or seasonal timescale from the public and the stakeholder in the coastal community. So we want to try to assess how good the seasonal forecast capability of the current generation of the seasonal forecast system, if we are interested in the sea level forecast. So a previous study has already used a dynamic model to do sea level forecast, but either they are limited to the tropics or a few limited geographic domain, or they use just a simple one member, or just a small limited ensemble. So here we want to expand the geographic domain, and also we want to include more model member in the ensemble. We'll try to get an idea how much improvement we can get from the ensemble, and also by comparing the model, we can get some implication for the model improvement if we are interested in the sea level forecast. And finally, we want to show some challenge if we want to have a usable seasonal sea level product in the near future. So this figure is from a paper by Vitosek 2017. So basically, decompose the high water level events into 4 parts. The top one is the wave run-up, which has the largest component to the high sea level part. The second is the tide part. tide is basically more or less accurately predicted use either harmonics method. The third part is the water level anomaly, which is the topic of today's talk, and also we try to use the GCM to forecast it. And the last part is the sea level rise. So in terms of the seasonal forecast, we can consider the sea level rise more or less as a constant across the 12 months or 24 months of time period in our forecast span. Like I said, we want to assess the model ability to forecast the sea level. So we use two data sets from the observation as a reference. So first is altimetry observation from this multi-mission data set, which is distributed by the CMS in Europe. And another independent data set we use is a tide gauge data from the Quantity Assessment of Sea Level Data Archive. The model we have right now is a 10 model from different operational center and also university. So the 10 model, 6 from the 10 model are from the NMME. There are 3 Canadian 4 from the Canadian Meteorological Center, CCSM4 from the University of Miami, CESM1 from NCAR, and CFSV2 from NCEP and NOAA, and GFDL CM2 from GFDL. And in addition to the 6 operational model, we have 2 model from the university, kind of like an experimental simulation. The first one is the CESM-UH. We run it locally at the University of Hawaii. We use the same model as the CESM NCAR, but we use different data set to initialize the model. And also the CFSV2 COLA from George Mason University. I think both of these 2 models use ORS5 instead of GODAS to initialize the model, directly compare to the CESM1 and the CCMs4 or CFSV2 NCEP. So because the ORS4 has altimetry simulated into their reanalysis, also the model analysis. So it can, we hypothesize that will improve the initial condition and also contribute to a higher scale in longer lead time. And the last 2 models are Access S1 from Australian Bureau of Meteorology and System 5 from European Center of Medium Range Weather Forecast. These 2 models are kind of more advanced models. So they have this ability to assimilate altimetry directly into their model analysis and initial condition. So this is the observed variability of monthly sea level anomaly calculated from the altimetry between 1993 to 2012. So this is a variability we are trying to forecast using our model. So clearly we see the highest variability or largest standard deviation is in this west boundary current and extension region, and also in the southern ocean part of it. These are both like eddy-rich region, and it turns out it's generally very difficult for the model to capture it and focus it. And the second largest part of the variability is from the tropical ocean, tropical Pacific and the tropical Indian Ocean, more or less related to the ENSO variability here. That part we have hope to capture it and forecast it. And another feature of this map is we notice that the variability of the sea level in the tropic or even northern and southern Atlantic is very low. So it's like 2 centimeters, which is also a challenge for the model to forecast it. And some part of the northern Indian Ocean is also has very low variability. As I said, we use altimetry and tide gauge as a verification. So we want to see how consistent between these 2 independent data sets. So the blue curve is the tide gauge observation. The red is the altimetry at that tide gauge location. By comparing these 2 data sets among these 14 tide gauge, most of them are very consistent. The correlation is high, above like 0.8 and 0.9. But some of the station the correlation is low. For example, the station A in South Africa here, the correlation is only 0.46. I think it's just because this eddy region here, and also some of the station has like an earthquake in the past, so which altered the tide gauge altitude, even the location, the rebuild the tide gauge location, so which degrade the quality of the tide gauge. But overall, I think these two data sets, even independent, they are pretty consistent and provide our more confidence when we assess the model against both of these two data sets. And finally, we have the dynamic model. We want to create a base benchmark to compare the dynamic model to. Here we use a simple damped persistent model. And what's shown here is the anomaly correlation of this model against the altimetry observation. We can see the most persistent part is in the tropic Pacific, and also some part of the tropical Atlantic also has some persistent skew. But because the Atlantic has very low variability, that variability or amplitude will be damped out very quickly. So at lead time, like 6 months or 4 months, 5 months lead time, only the tropic Pacific has significant correlation. For other regions, the correlation is dropped below the significant level. So now let's look at the anomaly correlation specifically for 3 model we choose here. The first row is CFSV2, the second row is CFSV2 COLA, and the last one is a System 5 from European Center. So if we look at the left column is the lead zero scale in terms of anomaly correlation. So if you look at the CFSV2, we have scale across this tropical band, especially the highest scale is realized at tropical Pacific, some part of the tropical Indian Ocean. For the Atlantic, it has some difficulty to have significant scale. But in the CFSV2 COLA, the simple difference between these two models is just to use different initial condition in the model. So we have improved the scale for both the region, and also the significant scale expand further into the higher latitude. So we basically think that a better initial condition or better initialization explains the higher scale. For the System 5, the model is more advanced, has higher resolution, also the assembly altimetry. It's slightly better than the CFSV2 COLA, but both of them are better than the CFSV2. This difference will also persist into the longer lead time. If we look at lead 6, we have, even if the correlation is low, but we still significant correlation in the tropic Atlantic, but that's non-significant for the CFSV2 here. And also same story for the System 5. So we kind of hypothesize this better initialization in this CFSV2 COLA contribute to the higher scale because they are both the same model. The last column is also scale of lead 6, but instead of comparing with observation, we compare with the model analysis. Since we don't have the model analysis for all the model, so we use a simple member at lead 0 as a proxy as a model analysis, which turns out to be very well correlated with actual model analysis for some of the model. So we can see the scale is higher, which is not surprising because I think the model lead 0 forecast I already realized some of the model error. So it's more or less internal to the model. The model is more or less forecast itself, but it's not purely that because it still have initial condition in the lead 0. So, but if we compare all the model, the difference is very small. Actually, the CFSV2 has lower scale than the CFSV2 COLA has lower scale than CFSV2, which is opposite to the first two column we saw here. So that means the model error is basically occurring in the very first month or even in the analysis, when it's compared to the model compared to the observation. So then if we show all the model together, which is a scatter plot from of the scale of lead 0, which is the axis, and lead 6 for the y-axis, and all the different colors show different model. The scale is average over the domain, and this triangle is a multimodal ensemble mean. So we can see a clear linear relationship between the models. The model has higher scale at lead 0, generally has higher scale at longer lead time. Either that's due to more accurate initialization, or yeah. So, but if we look at this, especially this two, the CFS V2 Cola, it definitely has better skill than the CFS V2 Loa here. They have the same model. The only difference is initialization. And the triangle here, the multimodal mean beats all the model, especially for longer lead time. So we plot out the same scatter plot for, but for the each of the tide gauge station, we have 16. We originally have 14, but we add this Santiago, and which are square here, and also the Charleston, which are star, which both the lower rise pilot sites. We're trying to compare the scale here. So we still see a clear relationship here. So basically, I think that kind of this plot generally not saying that better initialization, because here is a more multimodal ensemble mean, but it more or less tell us the model error is realized in the very beginning of the integration. Basically, the first month, the model error has makes the scale dropped significantly to the level, and it will persist to the longer lead time. Now we want to see how much improvements we can have if we have this multimodal ensemble mean here. Also, it's a scatter plot. The x-axis is the multimodal mean anomaly correlation. The y-axis is a single model correlation, and each of the dot is the scale at each of the grid point. So the red, the orange is the lead 0, and the blue is lead 6. So the value we're showing here is the percentage of the grid points that the single model beat the multimodal mean. So if the number is small, which means there is more grid points, the multimodal mean improved over the single model. So, but one thing we can see across all the models, generally, even the best model, the System 5, we still have like 37% grid points. The single model beats the multimodal, which is that there are 63% of grid points. The multimodal mean is better. For the left 6 model from the NMME, the value is smaller. We need one exception of the CSM1. We don't know the reason, but generally this 4 model is better than the 6 NMME model, but also the multimodal ensemble mean beats the single model. Even for the best System 5 model, we have more improvement over more grid points across the domain. So we also see the seasonal dependence of the scale. So here, the left column is just the multimodal mean scale, but each row is from different initial time. So the first row is January start targeted at July, and the second is April start targeted at October, and the third is July start targeted as January, and the last is October start targeted as April. So we can see that possibly due to this spring barrier issue from the ENSO prediction. So if we start from July, we will tend to have higher scale at the winter time compared to starting from January and targeted July. But this is also the same tended seasonality for the damped persistent model. So in terms of damped persistent model, we will have better persistence if the ENSO is growing, but instead of it's mature in the winter. So that the improvement over this damper persistence, the seasonality is reversed. So we see mostly improvement over actually the January starts. This seasonality also is related to the coastal tide gauge location. Like I say, that we show 3 tide gauge here. The left column is Nahola, California in the west coast. The middle is Honolulu, and the right is Port Fort Pulaski, Georgia in the in the east coast. So first, I think the west coast show the strongest seasonality of the skill because of its tightly associated with ENSO. So we see the highest skill realized in wintertime, no matter when we start the model. So for the Honolulu location, it's in the northern Central Pacific, so there is not too much seasonality. We didn't see too much seasonality. In general, this forecast uh, is higher. Forecast skills is higher than the damped persistence, which is the black curve, and the red and the blue curve is just the monthly and the seasonal skill, and the shading is a model spread. For the East Coast, we noticed that the skill is pretty low. So the model skill is dynamic model skill is generally not above this black curve, which is a damp persistence. But we see a small seasonality here. It tends to peak at late fall season. We don't fully understand why is that, but that show up in other analysis too. So the model has difficult to forecast the skill forecast the sea level variability, especially in higher latitude and along some of the coastal region. I'm not sure if it's because the model dynamics is a deficiency in the model dynamics. Here we try to understand the large scale pattern associated with tide gauge variability. The first row is the correlation between the tide gauge observation and the altimetry observation. So for the Honolulu here, so we see when the Honolulu has higher sea level, we tend to have a higher sea level along this upstream region, which is related to the Rossby wave propagation and also the thermodynamic forcing in upstream. And for the west and east coast, it's more or less related to this coastal trapped wave along the coast. When we do the same correlation but use the internal the model forecast or model simulation, it's better. So we see this similar pattern here. So which means the model seems to capture this internal dynamics very kind of quite well. Not very exactly the same, but I think the dynamics is captured in the model. But I think due to the initial condition error, so we cannot have usable forecast for, especially for the west east coast here. And then let's look at the real forecast what we can have from the model I showed before. So the blue curve is the tide gauge observation, and the red dots is just the forecast from the multi-model ensemble mean, and the shading is just the model spread from this 10 model. So among these 14 tide gauge location, we only have 9 location with significant R, and 6 of them are from the tropics. For some of the location, you can see like the location A, which is South Africa, it generally cannot the model cannot generate enough variability at all compared to the tide gauge observation. So the last 2 points I want to make here is, so when we do the model assessment, we remove the long-term linear trend from both the model output and the observation. So the left panel is just the observed linear trend from the altimetry between 1993 and 2012. We see a clear global mean sea level rise. Among these 10 models, only the 2 last model, like Access S1 and System 5, has the ability to simulate global mean sea level rise. Other 8 models generally strictly enforce the statistical approximation, so the global mean sea level cannot change. But that's okay. But the other issue is here. For example, if you look at the North Atlantic, the model has very different trend over this North Atlantic region. So that will, if we don't remove the trend, the scale will be or either boost or reduced if we include trend in the verification. So here I group the models into two groups. One is the two model which can simulate the global mean sea level rise, and the other 8 which cannot. So we put them together, and then we calculate the scale either with the trend or without the trend, and then we subtract them, get the difference. So for this two model which can simulate the global mean sea level rise, if we include the trend, it kind of get scale boost over the Atlantic, which means that part is due to the global mean sea level rise, because the 8 models doesn't have that or either have a wrong trend. So when we include trend, it just get negative scale impact here. For the Southern Ocean, I think it's more or less regional trend. Most of the model can capture it, so that will boost the trend if we include that trend in the verification. So the last point I would like to make is, because all the model generally the sea level component doesn't feel the atmospheric pressure. So in the analysis we include that IB effect, inverse barometer effect. But if we remove that effect, we can see the part which has most influence is in the high latitude. We can get a higher scale if we get a correct atmospheric pressure forecast and add that back to the sea level. But that's the upper limit of this correction, because the atmospheric pressure forecast is not perfect. Probably is worse than the sea level in some parts. So to conclude, so we assess all the models in a multimodal ensemble mean sense. So we see that the multimodal mean outperforms single model in most region, but not so much in the coastal region. And the better initialization, especially when we assimilate the altimetry, seem to improve the forecast. The best skill we can have is limited to the tropical Pacific and the Indian Ocean. The poor skill is found in higher latitude. There is a potential to combine this IB effect in the sea level output to improve the skill, but there is also challenge for many of this coastal region, which require to do post-processing and downscaling. And last, I show a slide from our recent results. So here we use a simple linear regression method to downscale the model output from a 6 model for a 6 seasonal forecast models. So the solid curve is the ensemble mean scale, and the shading is a spread. So red is the downscaling, and the blue is the interpolation. The open circle at this lead time showing that the difference or the improvement for this tidal gauge is significant. So we pick 3 tidal gauge for the west coast and 3 for the east coast, and we calculate scale. It turns out that for most of the location, just this simple regression can improve over the simple interpolation. So that gives us some confidence if we use more advanced method or combine them together, we can get some useful forecast for the coastal region in the future. And finally, I would like to acknowledge my co-author in the paper I mentioned. I thank my supervisor at CU, Dr. Newman, Dr. Shin. That's pretty much I have today. Thank you.
Thanks, Xiaoyu. We'll open it up to questions from the audience. You can either use the raise hand feature or just unmute if you'd rather do that. It's a small enough group.
Xiaoyu, I will ask the question. Thank you for a nice talk. For most of us, we're not very familiar with the definition of the sea level, how you calculate sea level. You mentioned at the beginning introduction slide that it has 4 components, including I only remember water level, and then you mentioned the sea level rise was not a big concern. And so could you please explain a little further, because these components, whether these components are included in different models.
Okay, so I think the model generally don't have the wave part, and also doesn't have the tide part. It only have this water level anomaly, and the sea level rise. We kind of excluded for that in our assessment. But among this 10 models, only the last 2 can simulate this sea level rise, but we specifically exclude that. And in terms of this other 2 part, the tide part, because we use monthly average data from daily data, which kind of remove the tide away. So we don't have that in our assessment. And also the altimetry is monthly average, so more or less the tide has been removed. But the wave part, I am not so sure. So I'm not very familiar with the wave part. But it's more or less, I think it's more impacting the coastal region for that purpose. But for the open ocean, I think maybe that's not so much important. I actually don't know.
Yeah.
Yeah.
I only heard the oceanographers talking about adding the wave component into CSM, but I'm sure in CCSM4, I'm not sure CCSM4 has that.
I don't think they have that.
Yeah.
But I mean, but the question is, how can we remove that from our observation? We didn't do that.
Yeah,
It's
and
not
also
right.
this is related to another question. What are we trying to predict? Which component we're trying to predict? You mentioned the predictable, more predictable. I don't think you use the exact word, but I had the impression that the ocean Rossby waves part is more predictable. But I just have the impression that maybe for applications the say how big is that component compared to say the storm surge, the large variability, and it just I just need more education on this topic.
Yeah, I think here we are what we are trying to forecast is just the third part, the water level anomalies, but we don't have the storm surge in our model. So that's not something the models are capable to do. We can forecast the large scale pattern here. Yeah.
Thanks.
But in terms of what we are trying to do right now is we want to include more effect like the local process, which is not related to large scale pattern. We want to approach that from a statistical perspective instead of directly use the model, because the model doesn't have that capability to do that.
Xiaoyu, I have a question. This is John.
Hi.
One thing related to what Haiyan was mentioning, I think, would be sometimes the correlation with storm surge is inherent in the other model statistics. For example, ENSO, right? ENSO actually increases a lot of storms along the East Coast. So maybe that correlation between ENSO and storm tracks and storm frequency makes its way into the skill of predicting the sea level anomaly, because right, those anomalies are made by averaging the water levels from the storm. So if storms have a lot of surge, you'll have a higher monthly anomaly.
Yeah, that's possible. Also, a while ago, I think maybe the large scale pattern alter this, like you said, the storm track or the cyclone track. which can contribute to the storm surge statistic to the East Coast. But that part, I don't think that's included in the model. But again, maybe some statistic measure can implicitly include that effect. That's what we are trying to do in the future.
I do have one quick question on, you mentioned in the presentation the lead 0 plus the lead 6 month. Was there a particular reason why 6 month? Did you see a limit of the skill, or was it just a good number to go from kind of the springtime to the fall, or the winter time to the following summer, etc.?
There is no specific reason. The only specific reason for that is among this 10 model, I think one of the model, the Australian model, only run the model to 6 months, or some start and run to 6 months, some start and run to 7 months. So we pick the shortest one just to have when we have the ensemble mean, we have all the models.
Makes sense. Thanks.
Mhm.
Hi, Xiaoyu.
Hi.
Yeah, I have a question regarding you have at the very beginning you have shown the observed variability, and there's a very large variability in the mid-latitude, especially also crucial and the Gulf Stream region. So, but the model has a much lower prediction skill than that of tropics. So I'm just wondering whether this is due to their potential predictability is relatively lower than tropics, or due to some other things like the model deficiency. Especially you have mentioned that the model has probably low resolution, cannot resolve the ID. If we have an ID result or ID permitting model, whether that will help the prediction or this subtropic regions?
I think due to both. So this figure I'm showing here. So the panel A, the top left, is just the figure I showed before. It's just the observed variability.
You'll have to share again. So the top left panel A is just the same figure I showed in the slides. It's observed variability. So among this 10 model, we can see the axis one actually captures the variability pretty well. It has this boundary current and extension, and the CS1 doesn't have any of that. So that's first reason I think the model doesn't have the ability to simulate the eddy activity and the strong variability. But even the model can have that, we cannot initialize the model correctly. So I think the XSS1 and the System 5 initialize the model with altimetry. But if we compare the model analysis or initial condition with the altimetry, the correlation is still very low in this region. So I think that my understanding is when we input that information in the model just rejects it, because it has to be some consistent way to absorb this information. The model cannot absorb the full information from the altimetry. Another issue is this eddy is probably not predictable at all. It's more like the weather we have in the atmosphere. So it can predict the statistics, but in terms of the phase, I think the model doesn't have the ability to do that. But for now, I think the issue is from both.
Okay, thank you.
I have a question. This is Erin Towler. Hello.
Hi.
This is also for the larger group. You know, I was just thinking about metrics that you're using, and I think ACC is great to use. I was just thinking and curious if there are other metrics that might also be good for this. I'm thinking of maybe coarsening it to make it maybe easier for the models to do well, like a categorical above average or below average or median, if you or some other threshold to see if the models do better with that. If you've looked at that, or if people have ideas for other metrics that might be more useful.
Yeah, that's something we were thinking about, but never had a chance to do. But one challenge, I would say, for example, if some of the location, the model generally cannot generate the variability, so that probably will not help. But for some location, if kind of relax the requirements of this anomaly correlation, so maybe we can have more useful product if we build our forecast from the current model output.
Okay, I see now that Michelle has her hand up. It's been very polite. So why don't you go?
I didn't. I don't even know if I have a good question, so I wanted to put it on a lower tier. So you mentioned over on the Atlantic side, so the east coast of the U.S., that skill seems to be higher during the fall. Is that for fall targets?
Yes. So for this location, for
Okay.
the Georgia, so we can see if we start from January, the lead 9, it's like September,
Mhm.
and we generally see that. But because the skill are very low, so that difference not sure it's significant or not. But we just see that trend, and yeah, I think that's I couldn't remember exactly, but I think it's due to just simply that variability during that season is larger. Don't know.
Yeah,
Yeah.
I was kind of wondering. I mean, you showed a really good map of the variance in the ocean, but I was kind of wondering about the atmospheric variance, especially since being an East Coaster, we usually have these in the late summer, early fall, the North Atlantic anticyclonic circulation tends to be very strong, at least as of late. So I'm wondering if there's a level of persistence in that ridging that the models might be getting some skill from. Of course, that depends
Oh,
on how much it impacts the sea level rise subsequently, but it was just something that crossed my mind.
oh, that's a good suggestion. We definitely will need to look into that.
Okay. It's nice talk, though.
Thank you.
This is really interesting talk.
Thank you.
Okay, and I think we've kind of hit the end of our open session. So let's thank Xiaoyu again one more time. However you want to applaud.